This is laboratory number 6, detecting signs of chemical change. Before you attempt this lab, you should read the first parts on background information, and you should read the entire procedure all the way through. You should attempt the pre-lab assignment, and all the information that you need to answer the pre-lab assignment is in the background and in your textbook. We may look at those just for a minute, but first I need to prepare, and that is glove up, and there's a step in here that's going to take some time. We need to clean the glassware, preparing the glassware. It says wash 12 test tubes with soap or detergent solution. We're going to use Dawn. Thoroughly rinse each one with tap water, and 5 mils is a minimum, so if you use more than 5 mils, you're doing well. 3 times with tap water. Then thoroughly rinse with distilled water, deionized water. Our water is distilled. Then dry the test tubes with a paper towel, and we're going to invert them in the rack and let them drain. This is to be certain that our glassware is clean, so the reactions that we witness in these various experiments for chemical change won't be contaminated. So we're going to do that first because it takes so long for the glassware to drain. We'll do that first, and then we'll move on to something else while that's draining it and come back to the lab after the tubes are cleaned. So, first thing I want to do is create a little soapy water. Like that. And we're going to add some Dawn. A little bit goes a long way. And then our test tube brush we use just to mix it up. Okay. Now we're going to clean each of our test tubes. And we need 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's use the same size tubes wherever we can. 11 and 12. Okay, so we'll clean all these tubes. This is the tedious part. There's no chemist on this planet worth his salt that hasn't cleaned his own glassware. Any chemist that has never cleaned glassware should never be gainfully employed in chemistry. Okay, we're getting there. Now, why am I not bothering with the outside of the tube? Well, if we had the time, we would clean the outsides of the tubes, just to be thorough. But since the reactions are only going to occur on the inside of the tube, we just need to be sure that we don't transfer any contaminants from the outside to the inside. Okay, 3 more to go. Number 11. And number 12. needless to say, these things get slippery when Dawn gets on the outside. Alright, so we're going to set that aside because we might need it again. Tap water. Alright, that's just what it says. Don't want it to run too fast. We'll just make a huge mess. And these laboratory faucets are notoriously leaky, so we'll make this as quick as possible. Now, I know the method says use 5 milliliters of tap water 3 times, but it's been my experience that it takes more than 3 rinses to get Dawn off your glassware. So we'll wait till there are no more bubbles produced. There we go. In fact, we can speed this thing up. We'll do multiple tubes. Then we only have to dump once for 3. Still getting bubbles in those 2. This may seem like a waste of video time, but I think clean glassware is so important that we're going to make the sacrifice and show the whole procedure. This is what you would be doing in the lab if you were here in person. Okay. All right. Let's see if we can do 4 at a time. Then that'll leave the last group of 4. All right, so we need to hold them solidly. Still getting bubbles. Remember, this is the only first rinse with tap water. Then we have to go through this and rinse with distilled water. And if you do the tap water rinse correctly, it won't take very much distilled water. We fill the tubes up for the tap water rinse because we're diluting the Dawn as we go. And the more dilute we get, the less there is left behind. That's probably, those 4 are good to go. Now we have 4 more, and we'll be done with the tap water rinse. Let's try this. Let's blow some of those bubbles out like that, and like that, like that, and like that. Okay. Now, speaking of clean glassware, if you're running a laboratory and you've got hundreds of these tubes and hundreds of pieces of glassware to clean, what do? Well, you could hire somebody to do it for you and train them and just hope that they stick around long enough for you to complete your research project. Or there's been some talk of dishwashers, mechanical dishwashers like we have in our home. So what are the hazards of that? Well, actually, there are a lot of pluses for it. Means your glassware will be washed the same way every time. But what procedures are usually employed in cleaning glassware? Well, you have a soap rinse, of course. Then you might have a tap water rinse that's in the dishwasher. And then you would always follow it up with distilled water. Okay, there's the problem. Distilled water, you don't want the inside of your dishwasher to contaminate your samples. So you're tempted to construct the inside of your dishwasher out of stainless steel, because stainless steel doesn't corrode. Well, I've got news for you. Distilled water is very corrosive for metals. Why? Because there are no metals dissolved in it. So the metals naturally want to migrate into the distilled water. So it does two things. Contaminates your glassware with metals from the stainless steel, and eventually it eats holes and pits in your stainless steel dishwasher. So what do? Well, there's one possibility. You could coat everything on the inside of your dishwasher with Teflon. And there are manufacturers that do that. But believe me, that is a very, very expensive alternative. So you need to have lots of private funding, or you need to work for a government, like the U.S. government, that has more money than they know what to do with, to buy you that. So that brings us back to hand washing. That's the only way to be sure that your glassware is getting clean. Now, that's the tap water rinse. We'll turn this off so it won't leak anymore. Now, for the distilled water rinse, we're going to use a wash bottle. Instead of measuring out 5 milliliters for every tube, we're just going to give it a good rinse. And when we use tap water, we were trying to dilute the soap as we went, each time we rinsed. But now that the only thing in there is tap water and soluble contaminants that it contains, the rinse is now a surface phenomenon. We only need to coat the surface. We're not trying to rinse the air. We want to rinse the tube. So we'll rinse down the outside a little bit, and then we'll do the inside of the tube. And I always like 3 times. That's a nice odd number. Actually, it's a prime number. That makes it even better. And we'll do that for multiple tubes when we have sure hand grip. That's 1. That's 2. And this is 3. Let's see if we can do 3 at a time. See how my grip is. See, we got a little soap on the outside, so we'll be sure and rinse that down. So the last thing we want in our sample is Dawn, unless it's supposed to be there. There's some lab procedures that I've used in the past where a little bit of Dawn was desirable for various reasons, or some type of surfactant, we call it. Surfactants break surface tension so that the components of a liquid don't just sit beaded on the surface, but actually dissolve in one another. And there are various surfactants created for scientific purposes. Some of them actually are used in the food industry to make foods not clump up. like ice cream. Right. If you read labels like I do, then you're liable to find lots of stuff that you don't know about. So you take those names and you look them up. That's only if you're curious. If you're naturally not curious person, then in my way of thinking, you will lead a dull life. But we're all adults here. That's your decision. Chemistry is much more interesting and much more understandable if you have a curious mind. Two more to go. And then we let them drain while we do something else. All right. Okay. That's the cleaning step. So we'll set those aside for a moment and keep our work area as clean and dry as possible. It's a little difficult with leaking faucets, but we'll do the best we can. Okay. I'm going to be doing this a lot. I better bring the trash can over here close to me. There we go. All right, so while that's draining, that was Roman numeral 1 in our procedure, step number 1. And we'll label those tubes as soon as they're dry, or near dry. And while they're doing that, we'll go to the pre-lab questions. And I'll give you a hint on some of these. You may even get the whole answer. So, briefly describe the hazards associated with solutions of 1 molar hydrochloric acid. HCl is hydrochloric acid when it's dissolved in water, and that's what they're implying here. So what are the hazards of 1 molar hydrochloric acid? Is that concentrated? Is it dilute? Or is it somewhere in between? Well, it's actually somewhere in between, because concentrated hydrochloric acid out of a laboratory bottle is about 12.1 molar. Right? So 1 molar hydrochloric acid is diluted a little more than 10 to 1. But it's still a strong acid by our definition. If you remember the lecture on, well, you may not have gotten there yet, but a strong acid by definition completely dissociates in water. So it produces protons and the counter ion to the proton. In this case would be chloride. And the acidity that is produced is due to that proton, that hydrogen ion. And 1 molar HCl is very, very low pH. So, and by definition, by OSHA and EPA definitions, 1 molar HCl is corrosive. So, what do corrosives do? Well, they attack metals, and they attack your skin. And if you are unlucky enough to get some splashed in your eyes, or breathe it in your mouth or your nose, it will damage mucous membranes. How about ammonia? 1 molar ammonia is fairly concentrated, and it's easy to detect the odor too. So you know you're near ammonia with 1 molar ammonia in solution. It's very volatile, so you can breathe it in, and it's also not low pH, but it's high pH. Ammonia is a base. So high pH is also on the corrosive end of the schedule for OSHA and EPA. The difference is that it's not acidic, so it generally doesn't attack metals, at least not quickly, but it is damaging to skin and the mucous membranes. Similarly, 1 molar sodium hydroxide is a very strong base. Sodium hydroxide is a strong base, and 1 molar is concentrated enough to make it corrosive. So you get similar damage if you come into contact with it on your skin, eyes, or mucous membranes. So, number 2, briefly describe the meaning of each of these phrases as it pertains to this experiment. The solution turned blue, but remained clear. All right. That is described on the very first page. We're talking about chemical changes. All right, so what do we mean when a chemical change? What are indicators of a chemical change? A chemical change is indicated by perhaps a color change, or evolution of gas, or it may get hot or cold, or you may form a precipitate. So what's a precipitate? A precipitate is a solid that forms after you mix 2 solutions together. The 2 solutions are completely clear, no solids. So when you add them two together and you get a solid formed, a chemical reaction has occurred. All right, so let's go back to the question. The solution turned blue but remained clear. So what does that mean? That means that it's no longer colorless, or it did change color, but it's clear, which means you can see through it. It's not cloudy, which means there's no evolution of very fine gas particles. There's no formation of solids. It remains clear. There's a difference between colorless and clear. 2(2). The reaction is endothermic. So what do we mean by endothermic? Well, thermic refers to heat. Exothermic means heat moves out of the system. So you can feel it as warmth. Endothermic means heat moves into the system, which means you can feel it as cold. The third one, a precipitate formed. I described that to you already. What is a precipitate? The change that occurred was physical and not chemical. So how do we know we have a physical change and not a chemical change? A physical change requires to begin with, the most obvious physical change would be a change of state. For instance, if water freezes, that's a physical change. Or if water vaporizes, that's a physical change. Or if water condenses on a cold pipe or on a cold glass of drink of some kind on a hot summer day, that's a physical change. So, and there, in step number 3, we are asked to describe what would be a chemical change or physical change relative to these 3 scenarios. On a hot day, drops of water collect on the outside of a glass holding iced tea. I just told you that one. The second one, clear, colorless lemon juice is added to a glass of iced tea. The tea color changes from brown to yellow-brown. What has occurred there? Is that a physical or a chemical change? It may be chemical, but more likely, all you've done is diluted the brownish color due to tannins in the tea with some solution, lemon juice, to make it, rather than brown, yellow-brown. Now, it's entirely possible that a chemical change has occurred because lemon juice is an acid, and it could react with something. So either is possible here. Number 3, water is added to a glass of iced tea. The tea color lightens. That's obviously a physical change because water is not going to react with tea. It simply dilutes the color. All right, those are your pre-lab questions. Now, in this procedure, we're going to label our tubes and have 12 different laboratory assignments labeled A through L. And we're going to conduct those laboratory assignments in each of the 12 tubes that we just cleaned. But we have to label the tubes so we don't get them mixed up. And the instructions are here. We'll go through them one by one. And then as you make observations, they go in the data sheet. And you're going to make observations in column 1. And to the right of it, did a chemical change occur? And you're looking for signs of a chemical change. Did a color change? Did we get gas evolved? Did we get a precipitate? Or was there heat evolved? And sometimes you get multiple indicators of a chemical change. Okay, so now let's see if our tubes are dry enough to label. If not, we'll help them along with a paper towel. Let's move over here. Okay, so let's see. If you hold it strongly and shake, right, and we want that outside to be dry. But we're going to shake as much water out of the inside. And all of these reactions occur either in aqueous solution or I think one has ethanol involved, but ethanol is also starts in an aqueous solution. Okay, I think I'm shaking out enough water so that we won't dilute our mixtures terribly much with the water that's left in the tube. Okay, so now we want to label each tube with a grease pencil. And let's see if we can do this. That's an A. That's an A. This is going to be a B. If I make it strong enough that I can see it, I might have to hold it up to the light to see it. This is C. And this is D. Find a place where it'll stick. That's not working too well, is it? There we go. E. Pretty, you just have to be able to tell the difference. E, F. G. H. That didn't show up very well. Let's try this side. And I. And J. And K. And L. All right, we're labeled. Now, we're going to need some things. We're going to need graduated cylinders. These are 10 milliliter graduated cylinders. We're going to need some place for them to drain, because whenever we use one, then we rinse it out and invert it so that it can drain before the next use. All right? So, what we'll do is we've got all our reagents set up over here in this location, and I've organized them so that they're grouped. Now, sometimes we have to borrow reagents from a previous exercise, but we'll follow the directions, and this keeps us more organized, and the better organized you are, the less likely you are to make mistakes. Okay, so now, let's see, what do we need first? The first experiment is 0.1 molar cobalt 2 chloride hexahydrate in 95% ethanol. So what does that mean? Well, let's look at A. Let's see. Here we go. Cobalt 2 chloride. Okay, in this one we're going to transfer a small amount of cobalt 2 chloride with a microspatula to a dry tube, and then add 2 milliliters of 95% ethanol to the test tube and record our observations. All right. So let's do that. Let's get cobalt 2 chloride and 95% ethanol. And we're supposed to use 2 milliliters of the ethanol. So we're going to try to do this. Let's use the wider mouth. Let's get 2 milliliters in here. And it only has to be approximate. This is known as qualitative chemistry. We're not actually going to measure. Results will not be in the form of numbers or that type of data. Okay, so we need our A test tube, and we need some cobalt 2 chloride. Let's make an observation here. Let's see. Here we go. Cobalt 2 chloride. Notice that the solid form is kind of a reddish color. All right, so let's put it in our tube. And observe that it's red. Let's see, a white background, that's good. White background is best. And then let's add some of this. Okay, now what has happened? And how do you mix? You hold it firmly at the top and tap it. All right. I don't think all of it got down in there. I think some of it is still sitting up here. All right. All right. There we go. So what happened? We went from a red color to a blue color in 95% ethanol. So let's make that observation. A color change from pink, actually red, to blue. Did a chemical reaction occur? Well, based on our theory that a color change indicates a change in a chemical change, then yes, I would say we did have a chemical change occur in that process. Now we need to clean our utensils. All right, clean the spatula. And here we go. So the spatula is clean. We're going to rinse out. Actually, we only had 95% ethanol in this one. So let's just turn it upside down. And the ethanol is very volatile. It will dry out on its own. So that was A with cobalt 2 chloride and ethanol. All right. Let's see. Now, we need 1 milliliter of cobalt 2 chloride in ethanol that's already prepared. So we need 1 milliliter of that in a test tube. That's our B. So 1 milliliter of, let's try this one. It might be easier to control. This is the same solution that we just made, only this is more of it. So let's use this one since it's already clean. So we need 1 milliliter. 1 milliliter. Okay. And let's put that in our tube. Here we go. And let's rinse it out. And then we'll add 1 milliliter of distilled water. So we need 1 milliliter of distilled water. Let's see, this has already been cleaned with distilled water. Let's just add a ml here. Here we go. Now, this is the B tube. Let's see what happens. Let's get a white background. Whoa! We went from blue to pink simply by adding water. Okay? So, you did get a color change from blue to pink. And color change indicates a chemical reaction. A chemical change has occurred. All right. Now we're moving on to C. I'm going to put these down here so that we don't get mixed up. We've used those two. Now we're moving to C. And for C, we need zinc metal and 1 molar hydrochloric acid. Transfer a piece of zinc, about the size of a half a pea, to the C tube. All right, so let's see if we can do this. I'm going to see, do we have any tweezers in here? Yeah, those are kind of rusty. I don't want to contaminate our sample with that. All right, I got an idea. Rather than reaching in, there we go. Now we can put this into our C tube. About the half a size of a pea. And that looks good. There we go. Now I'm going to do something that I should never do, but I know this is a clean-way boat, so I'm pretty safe in putting it back in there. All right, so the next step is add 2 milliliters of 1 molar HCl. We talked about 1 molar before. It's corrosive. But we need 2 milliliters, approximately. All right, so 2 milliliters. Oop, that's 4 milliliters. Let's try that again. Okay, that's good. And let's add them together and see what happens. Zinc and 1 molar hydrochloric acid. Mix it up good. And let's see. I'll bring it a little closer. Maybe you can see that from this angle. So what's happening? Well, we don't want to mistake bubbles from a reaction to air bubbles that were trapped on the way in. So let's shake it up and break off all the bubbles that may be attached to that zinc, and then look to see if there is any more gas production. Now, I'm not sure if you can see it on the video, but if you look closely at that piece of zinc, you'll see bubbles are forming on the surface of the zinc. In fact, you might even see some rising. Oh yeah, they're getting bigger. So let's see. Let's move over here with a different background. I don't know if that's any better. Let's try this one. Here we go. You got some pretty big bubbles. So let me set that down for just a minute. And one of the observations is that a gas is formed. That's definitely a chemical reaction. But what happens in a chemical reaction when a gas is formed? Well, we couldn't say for sure without actually measuring the mass of that bead of zinc. But I would be willing to bet that as the gas forms, zinc is transformed, the metal, into a zinc ion, which goes into solution. And if that is indeed what's happening, then the mass of the zinc should decrease. Okay, so that's C. Now let's be sure and rinse this out because we had hydrochloric acid in there. All right, just a little bit like that is not going to be a problem down the drain. All right, so that was C. D, zinc and copper sulfate. So we need zinc together with 0.1 molar copper sulfate. All right. So in tube D, we transfer a piece of zinc to the tube and 2 milliliters of 0.1 molar copper sulfate this time. Let's see, maybe I can do it with one. Oh yeah, I got lucky. There's one little piece that goes in D. All right. Now we need 2 milliliters of 0.1 molar copper sulfate. Let's see. There we go. Copper sulfate is bluish in color. It's clear, but blue. So now let's add that to our tube with the piece of zinc. All right. Let's get the bubbles off of that piece of zinc. So we don't want to mistake any trapped air for bubbles produced in a reaction. Okay, this reaction is going to be kind of slow. I already know that. So let's let it sit for just a minute and clean up. I'm going in the sink over here. There we go. And let's put these items back at the D location. Now, rinse off a spatula. Now let's take a closer look at D. What I observe is that the color, the zinc, the luster that it initially had, which was kind of dull, but it was a lighter color, has changed. It's getting darker. So we're actually seeing a change on the zinc itself. All right. So what's happening? Well, we had in the solution we have copper sulfate, and then as we what happens is over time, I don't think you can see it yet, over time the blue color will become less and less and less. And that's because the copper is being consumed. And what is it doing? The copper is exchanging places with the zinc metal. So the zinc is going into solution. Zinc sulfate is colorless. Copper sulfate is blue in solution. So if the copper in solution is exchanging with the zinc in the piece of metal, then the copper is being deposited on the surface. On the surface, I don't know if you can see that. It's being deposited on the surface of the piece of zinc as copper metal. And very finely divided copper metal, like most metals, if they're very finely divided, they initially look dark. Some gray, some black. So that's what you're seeing. You're seeing the copper being deposited on the surface of the zinc as it is exchanged in solution to a solid as the zinc solid becomes zinc ions. There is a chemical reaction there. That's D. All right. Ready for E, copper sulfate and hydrochloric acid. So E, copper sulfate solution and hydrochloric acid. All right. Let's get that out of the way. So what are we supposed to do with those two? We need a piece of zinc. We already did that one. E. Copper sulfate. And we need 1 milliliter of copper sulfate solution, 0.1 molar. There's 0.1 molar copper sulfate. 1 milliliter to tube A. So let's get some of this blue solution. 1 milliliter. Very carefully. The ratio is more important than the absolute, so if that's 1.5 mils, and they want 1 mil of HCl, we'll have 1.5 mils of hydrochloric acid to match the ratio. So there's the copper sulfate. Blue. Now we want, this one's been draining, hydrochloric acid. 1.5 mils. Since we went over on the copper sulfate, we'll keep the ratio the same with 1.5 mils of hydrochloric acid. There we go. All right. So we're a clear solution, but we're blue, right, for the copper sulfate. Now we're going to add hydrochloric acid. All right. What happened? Well, I don't see any gas. We haven't been feeling the others. There's no temperature change. And to be honest, there was no temperature change on the others prior to this one. So that one looks like it's still blue. I don't think anything has happened. It's still clear. It's still blue. There are no gas bubbles. There is no heat produced. It's not cold. I think that one was a change from blue to light blue by dilution only. That's a physical change. There's no chemical change there that I can observe. And that was E. Now for the cleanup. All right. And let's clean up this one. Clean up this one. There we go. Let's put these back in the E slot. Okay. Now for F. Copper sulfate. My paper's getting wet. Move it over here. For F, we need copper sulfate solution and sodium hydrogen carbonate, or baking soda. All right. So these are both in solution. Sodium hydrogen carbonate, 0.5 molar. and copper sulfate. So we need to move this one over here, these two together. Copper sulfate and sodium hydrogen carbonate. All right, this is tube F, and this is exercise F. So how much of F? We need 1 ml of copper sulfate and 1 ml of 0.5 molar sodium bicarbonate. 1 ml of copper sulfate. You know, I've got an idea. Let's see. Instead of using graduated cylinder where I make mistakes every time I try it, let me see if I can find a graduated transfer pipette. You know what? Let's bring this whole bunch over there. It says so many milliliters of this and so many milliliters of that. But if you maintain the same ratio, that's the important factor. So if we say for F, 1 milliliter of copper sulfate, 1 milliliter of sodium hydrogen carbonate, we want equal proportions, right? So if I fill this pipette up, and I know from experience that this is roughly 1 milliliter. So if I fill that up to a little more, there we go, fill that up, that's 1 milliliter, right, of copper sulfate. And then we'll use a fresh pipette. These are called transfer pipettes, and they're disposable. We need sodium hydrogen carbonate in the same amount. There we go. So let's see what happens. Let's hold it over here where we can see it change if possible. Oh, what's happening? Notice that? There you can see we've got a precipitate. Notice it's getting cloudy. Very cloudy. We formed a precipitate. All right, so what does that mean? Well, did we also form a gas? You may not be able to see it here, but those are just entrained bubbles, air right there. But deep down inside, I can see gas bubbles forming from this reaction. So we formed a gas, and we formed a blue precipitate. That's definitely a chemical reaction. It's a pretty reaction, actually. Tempted to do it again if we had time. That's F. G, copper sulfate solution and ammonia. So here we have more of the copper sulfate, 0.1 molar, just in a different bottle, and 1 molar ammonia. For G, now those are used, we'll deal with those later. Let's see what the ratio is on these two solutions, G. 1 milliliter of 0.1 molar copper sulfate to the test tube, and then 1 milliliter of ammonia solution to the test tube. Okay, so that's equal proportions. We'll do a similar thing to this as we did to F. We'll just use 1 full pipette of copper sulfate. We need a little more than that. There we go. To G. All right. And then ammonia. And this is like the stuff that you, or your parents, clean with. It's ammonia solution. And one thing about video, you can't smell it. But I guarantee there's ammonia in the air. I can smell it. So now let's add this 1 milliliter to that 1 milliliter and see what happens. Let's see, get over here where you can see any changes. Whoa! Not only did it get darker blue, you can see it's cloudy. We formed a precipitate. But it looks to me like the precipitate formed and then disappeared. All right, so it's blue, but it's clear. I think we initially formed a precipitate, and you can see that it's cleared up. So whatever precipitate we formed went back into solution. That is definitely a chemical reaction. It's even prettier than F. All right, that was 0.1 molar copper sulfate and 1 molar ammonia for G. Now H. H is magnesium and copper sulfate. So that's magnesium metal. And I've got little strips of it cut out here. 1 centimeter long of magnesium metal, put in a tube, and then we'll add 2 milliliters of 0.1 molar copper sulfate. Here we go. I've isolated it here. Okay, so we're going to take, let's see, can I do this with my fingers or do I need a, I've got some tweezers. Here we go. I got some fine tweezers. Pardon my arm getting in the way. Got some very fine tweezers here that I just remembered I had. So for H, we're going to take one of these 1 centimeter strips here and put it in H. Right there and then there in the bottom. So you can see it right there. Okay. Then we're going to add 2 milliliters of copper sulfate. So I know that these pipettes will hold about 1 milliliter up to the bulb. So we're going to have 2 bulbfuls. All right, there's one. Let's see if anything happens initially. All right, there's one. Okay, I want to be sure that we don't mistake bubble formation for entrained bubbles. So we'll knock the bubbles loose. Okay. I think we've got a reaction already. Let's put some more in there. There. And I think what you can see is little black flecks. Okay? That are forming from a reaction of magnesium metal with copper sulfate. So those little flecks, the magnesium is moving from the metal to the magnesium ion in solution, reacting with the sulfate, and magnesium sulfate is insoluble, and it forms those little black flecks. That's magnesium sulfate. And the copper is being deposited on the metal. Actually, that might be a mixture. Those black flecks might be some copper as well. All right. But we see there's a precipitate forming, and let's look at the metal there. That's better to look at it right there. It wants to float because it's got gas forming on it. Gas bubbles. Okay, we got gas formation and a precipitate. All right, so that was H. It started out light blue, and it's becoming less and less color. The magnesium's getting smaller. I can see that. It's losing its edges, forming a gas, and we're forming the copper metal as a process. You know, now that I think about it, I believe those black flecks are actually copper, finely divided copper metal, like we saw earlier. And the magnesium sulfate is actually soluble. So the magnesium sulfate is colorless in solution. Okay, let me say that again. Magnesium sulfate is forming as the magnesium migrates into solution and reacts to form magnesium sulfate. And the copper, which comes from the copper sulfate in solution, is forming the black flecks, which is actually copper metal. And gas is also forming. All right, that is H. So let's move IJ down here and KL right next to it. There we go. All right, we don't need the magnesium anymore, I don't think. Well, maybe we do. I think we do. For I, let's see what I says. Magnesium metal and hydrochloric acid. Yes, we do. So magnesium and 1 molar hydrochloric acid. So it's a good thing I've got another piece of magnesium here to put in I. Oops, dropped that one. Here he comes. Here he goes. Cover that up. And how much hydrochloric acid do we need? 2 milliliters of hydrochloric acid. All right. So we'll get a fresh transfer pipette. Isn't this easier, using the pipette than trying to pour the stuff? So there's I with our magnesium metal. We're going to use 2 milliliters. And let's see what happens. Is it a quick reaction? Whoa, yes it is. Very fast. Look at the gas formation. That may even be exothermic. No, I don't feel any heat. Okay, so it's not exothermic, but it's definitely lots of gas formation. And what's happening to the metal? Let's see if we can get a better look at it. I don't know if you can hear it if I get it close enough. I can hear it. There's so much gas being produced that it's a fizzing sound. And the magnesium metal is disappearing rather quickly. Oh, there it is, floating on the top. There it is. Okay. So what's happening? Well, the gas formation is, I believe, hydrogen gas, which comes from HCl. It has hydrogen in it. All right? Plus, we're in an aqueous environment. So we form hydrogen gas, and the magnesium is going into solution as magnesium chloride. So the magnesium metal is turning the magnesium ion, and in the process, hydrogen is being evolved from hydrochloric acid. And that's the bubbles. Hydrogen gas. Eventually, if there's enough acid, and I think there is, that magnesium metal strip will completely disappear. It will be consumed entirely. So that's I. All right. What's J? We're getting close. J is hydrochloric acid solution and sodium hydroxide. So here's sodium hydroxide, 1 molar, and here's 1 molar HCl. All right. So what happens? Let's see. This is J. All right. So I don't need my tweezers anymore, I don't believe. Let me put those back before I forget them. Okay. So how much of each one are we going to use in experiment J? Yeah, experiment J is hydrochloric acid, sodium hydroxide, 1 milliliter of each. So we're going to use 1 milliliter of acid with a clean transfer pipette. Here we go. And now we're going to add 1 milliliter of sodium hydroxide. So notice what we have here. We have a strong acid and a strong base. So you can probably guess what's going to happen. Well, we have what's called an acid-base reaction. Acid's already in there. We're going to add the base. All right. What evidence is there of anything that's happening? I don't see any color change, no precipitate. Let's see if there's any temperature. Oh, yeah. We got some heat here. This is an exothermic implies, or any change in heat implies a chemical reaction. So there we go for J, and there's J. See, it stayed clear, right? No color change, no gas evolved, no precipitate, only heat. And that's an indicator of a chemical reaction. 2 more to go. So K, hydrochloric acid solution, 1 molar, and 1 molar, 0.5, actually 1 milliliter, 0.5 molar sodium bicarbonate, sodium hydrogen carbonate. So here's our acid, here's our sodium hydrogen carbonate for K. And let me verify, K, 1 milliliter of each. So let's put the acid in there first, in K. Fresh transfer pipette. Here we go. Seal that up. And sodium bicarbonate. One milliliter of this. Here we go. Let's try that again. Picked up a bunch of air. Okay, let's watch what's going to happen here. Whoa, you can see, can you see? Gas bubbles. Immediately forming. That's it. The only thing that we see as evidence is formation of a gas. Evolution of a gas. Let's see. I don't feel any heat. So it's an acid-base reaction. Sodium bicarbonate is a base. Hydrochloric acid is an acid. So we should expect some heat production. It's just that I don't feel any heat. Right. But we did get gas evolved. And that's a definite indicator of a chemical reaction. Last one. Ammonium chloride solid for L. And 2 milliliters of distilled water at room temperature. 2 milliliters of distilled water. Okay. So ammonium chloride. And let's see. Let's use a small beaker. Here we go. And we'll just put some water in here so we can use our pipette. Our transfer pipette. Okay, that should be plenty. And that water is definitely at room temperature. So, we need a micro spatula. Let's see, here it is. And we're going to fill the spatula with ammonium chloride. Let's see if we can get a lump. Oh, that's okay. There it is. It's full. Transferred to the tube. All right. It was a lot down the sides of the tube. So what we'll try to do is when we add the water, we'll try to rinse it as we go. So this was how many milliliters of water? 2 milliliters. So we need 2 pipettes full. There's one. All right, so let's see if we can rinse some of this down with that milliliter. And then there's another milliliter. Finish rinsing down the best we can. And then we'll mix. So what happened to the solid? The solid went into solution. The solid is in solution, and it's cold. We actually had an endothermic reaction, right? So a change in temperature means a chemical reaction has occurred. Oh yeah, that's cold. So ammonium chloride solid in solution, in aqueous solution, decreases its temperature. All right. There. Those are disposable. We're finished with the water. And we're finished with that one. So that's A through L, all done, except for the cleanup. Now let's see if there are any other observations that need to be made. We have questions that have to be answered, post-laboratory questions, based on the data. Now, here's the best way to answer these, and I'll give you a glimpse at my key, is post-lab questions are actually up here. Okay. Here we go. When you answer these questions, you don't have to say, I put it in here from my reinforcement, is the reactions that occurred, because I know what they are, or what you're adding together. But if this question says, based on your experimental data, list the laboratory assignments that, 1, did not produce a chemical reaction. So you look down, which ones did not produce a chemical reaction, and there's a letter assigned to it. And as you're going along, as you're watching this video, you should have been recording your observations as I gave them to you under each one of the, in the data sheet, A, B, C, all the way down, observations and chemical change, did it occur, right? So you just look at these and you see which one, or more than one, did not produce a chemical reaction. And then all you have to do is use the letter for your answer. So your answer will be post-lab. So your answer will be whatever the letters are, right? And I know what the letters should be, right? So I just look at your answers and say, okay, you said E, A, B, and D, or something like that. I say, okay, that's right. That's partial right. That's all wrong. Did not produce a chemical reaction. I'll give you a hint. Only one of them did not produce a chemical reaction. So you can find which it is. Which ones produce precipitates? So you go back and look at your data table and say, which ones did we observe produce a solid when the reaction occurred? And you just list the letter for the experiment, or the assignment, they call it, the assignment, the letter assignment that produced a precipitate. Which ones produce gaseous products? Which ones produce gas changes? Which ones had a heat change, either hotter or colder? Then 2, based on your observations of the laboratory assignments that produced precipitates, can you conclude that solids form only when 2 solutions are mixed? Right? What do you say? Based on your observations, can you say that only when 2 solutions are mixed, precipitates form? And explain. Say, well, in experiment letter D or F or G or multiples, we observed that adding 2 solutions together did produce precipitate in those cases, And in that situation, only solutions were added. Did you see the formation of solid in others where two solutions were not added, where you added a solid of some kind with a solution? Then that would be contraindicated for this answer. All right. For 3, based on your observations of the laboratory assignment that produced gas assignment, can you say that each gas is the same? Maybe you can, maybe you can't. You have to look at what was added, right? If you think that hydrogen was produced by this reaction, and you thought that it was produced by a second reaction, well, then you've got to show where the hydrogen comes from. Did you add anything together that had hydrogen in it to produce the hydrogen? Or was it what other gases could form? Well, it's not hot enough to boil water, so what other gases could form? Well, the most common gases that are formed in chemical reactions that we would study are hydrogen gas and carbon dioxide. Right? For instance, if you look at sodium bicarbonate, sodium hydrogen carbonate, you see that that's got carbon and oxygen together right there. So that could theoretically produce CO2 as a gas. Okay? Or when we react metal with hydrochloric acid, like we did with magnesium and hydrochloric acid, we got bubbles. So what kind of bubbles would those be? Well, you wouldn't expect CO2 because magnesium and HCl, there's no carbon in there, right? So that was probably a different gas. But the only way to tell for sure is to have some other type of indicator that they are different from one another. And if you have a selection of either hydrogen or carbon dioxide, and let me go over to the board. It's easier to explain there. All right, so how do you tell the difference between two gases that are being involved in a chemical reaction? Well, one possible way is if you are pretty sure, based on the reactants that you add together, that the gas is either hydrogen or carbon dioxide, there's a very simple test that you can use to distinguish between the two, and it's called the glowing splint test. If you take a glowing splint that it's just a stick of wood that you light and then you blow it out, so it's still red hot on the end, which is enough energy to start a chemical reaction if one is available. So, if you capture the gases, you have either hydrogen or carbon dioxide, and you take the glowing splint and you stick it in the tube with hydrogen, it will pop. And it will pop because the hydrogen reacts with oxygen in the atmosphere and produces water. And it generates a lot of heat, and the reaction is very energetic, so you hear this popping sound. But if you put the glowing splint in the gas and it's extinguished, then you know it's carbon dioxide. Now, why is that? Well, think about it. Carbon dioxide is used in fire extinguishers, or some types of fire extinguishers, and it's used in those because it does not react in the atmosphere. In other words, carbon dioxide is as far as it's going to go. In other words, it's already reacted with oxygen. It's gone as far as it's going. It's not going to react any further. So what it does is it excludes oxygen from the splint, and the splint goes out. It just goes black. Okay, so that's one qualitative way to tell the difference between the two gases if you're pretty certain that it's either one or the other. Let me move this back down and see if there's anything else that we can learn from this experiment. That was, let's see, color change, heat. Based on your observations resulting in heat changes, can you conclude that heat is always released in a chemical reaction? Well, is it? Look back at your notes. Did we get heat for every reaction? And maybe some short explanation as to why not. Right? I want you to think. Thinking is good. Curiosity is good. This is not chemistry is not one of those subjects that you study and just memorize answers. If you're going to be an MD or emergency medical tech, then you do. You just memorize procedures so that you know how to do them quickly in an emergency. With chemistry, and with most of the sciences, you need to think and be curious. What if? Why does this happen? Ask yourself these questions. If you're not curious, chemistry becomes drudgery, and it becomes more difficult to learn. So, pique your curiosity. Look for answers. Okay? That was it. That's it for this experiment. And I know it was a long one. It took lots of steps. So this video is going to be long. I know that. Now we just have the cleanup. I need to clean up the tubes, right? Clean the markings off of them, rinse them out good. I've got some soap water. I'm going to finish that. I'm not going to bore you with that on the video. Then I'll dispose of these tubes and put the chemicals away. And we'll be done. So that's the end of that, and good luck.